Can someone say hi so I can test my audio?
Hi.
Thank you. It's working. See the green? That gives me confidence. Okay. Anywho, so I have homework 3 up. Welcome back, folks. Happy Thursday. Nice rainy Thursday. I'm sure some of you are happy to not be out in the rain if you can help it. I did get a couple of questions about homework 3, and I wanted to offer the opportunity for you guys to ask questions as well. One thing that a question I answered yesterday was at the end when you're interpreting the direction of things. There are choices for slope coefficients that say significantly positive or negative. And the question was, do I intend that to mean the sign of the slope, or do I intend that to mean what the slope does thematically? So in this example, the predictor is coping, the outcome is anxiety. So you would think that, better coping leads to lower anxiety, which is a negative relationship. But if you think of that from the perspective of coping being a beneficial thing, that's a positive like association. I literally just meant the sign. So don't overthink these. That's what I meant. The sign of the slope was what I was going for in these last few drop down questions and throughout. If I meant the intent, like if something is good for the outcome or bad for the outcome, then I would use choices like beneficial, harmful, something like that, that conveys more value than it does sign. So I was not intending that to be tricky. Let's see. Another thing that I added recently is a few folks have reported that their models in R have difficulty converging. If that happens, there's an option that you can try. That should make the results closer to what they are in SAS and Stata. But for this type of model that we're using, I don't expect too many estimation problems. That will be not the case if we go to generalized models or crossed models where there's more variance components or things that have to be estimated. So let me ask homework questions. Vladimir, go for it.
Hey Lisa, yes,
Hello.
I have a quick one now that you mentioned this convergence thing, because in section 2, I think that my model had some kind of problems to converge based on the element results. However, the numbers were correct, so that wasn't a problem to me. However,
Good.
when I added the interaction for section 3, the model didn't have any kind of convergence issue. Do you know why is that? To me, if the model is not working well, and if we add something else, that should be wrong again, right?
Not necessarily. By the time you get to the end of the questions, you all are fitting the population model that generated these data. So for
Okay.
that reason alone, it should work.
Okay, that makes sense.
Yeah, I honestly don't know. Some of the convergence errors I've seen in R appear even though the solution is identical to what I got out of SAS and Stata, and
Uh-huh.
they did not report convergence problems, and there's no evidence of correlations at a boundary or variance components that are at zero. So in those cases, I honestly don't know what it's reacting to.
Yeah, I checked those things and they were okay, so I didn't know, but the numbers were correct, so I just used them.
You
Thank
use
you.
the numbers. Yeah, they're the same numbers. They just were
Yeah,
reported without errors in the other software packages.
exactly. Yeah, thank you, Lisa.
Thank you. Who else? Questions on homework? Due Monday. I've looked in the database. It appears there are folks who have not gotten started yet, so I'd like to encourage you to do so. And by the way, if my face looks a little bit weird, I was at the dentist this morning getting a filling replaced, and the Novocaine is not quite worn off yet, so I've got a little droopy lip situation here, but I think I'm mostly cognitively okay. But if I start mixing up my words and things, I'm going to blame it on the drugs. When they shoot drugs into your face, right? That you'd think that would have some sort of impact on your cognition. But that's better than them doing it without any drugs, which is a horror I don't even want to contemplate. All right. No homework questions? Not yet? All right. Fair enough. Then, in terms of other things that you can be working on, I wanted to make sure everyone saw that both assignment 4 documents are now available. I posted them on 11/13, which is their due date. So I have a rubric for individual analysis of cluster data in terms of the features that I'm looking for your assignment. And I also had fun with AI the other day, building the alternative assignment, which I think about 6 of you selected this option, so not so many. Correcting, I have 9 questions that I submitted to either ChatGPT or Google Bard, and I have their answers. And I was not disappointed. I'm happy to report that my job is still safe. ChatGPT does not know everything that it needs to know with respect to multi-level modeling, so I will let you read those over and let me know if you have any questions on what you're expected to do. The idea is to read the prompt, try to determine what's accurate and what's inaccurate, and then describe that conclusion in your response. For the AI correction, I do expect you to edit this document. It's a Word document I gave you deliberately so that you could read the prompt and then type in your answers, and then I can provide comments. For the individual analysis option, that's a PDF on purpose because I don't want you typing in this document. I want you to provide a results section, like a manuscript, that you would use your typical APA formatting for those of you who are from psychology, or we use it in education. If you use MLA or some other type of formatting instead, that's fine. Just make it look like what it should look like to be a published paper. And I don't want the list back. I really don't. I want you to write a coherent document that has transitions and references to tables and figures and all of the things that you would have to do in traditional typical writing. If you want to talk strategy in terms of how to build your models or what to report, I'm happy to do that with you individually as well. So there we go. Yeah, so homework 3 due Monday. That way everybody can have a nice Halloween. And then formative assessment after that, and then homework 4. And then we're kind of in the downhill stretch in terms of the semester wrapping things up. And the reason, by the way, your individual analysis or written assignments are homework 4 and not the last one is so that you get a chance to revise them. So you will get a chance to correct any errors that I marked or any omissions that I marked and submit it by the end of finals week for up to full credit, along with one more assignment that I will release after we're done with the general ed unit. So that's what's still out here. I can't believe it's the end of week 10 already, can you? It seems like this semester has just flown by. All right, so I'll shut that down. Let's go to example 5 and talk about some cross models, shall we? So what do you remember from last time? What's a cross-classified model used for? Will we be able to revise AI corrections? Yes. Yes, anything written you get a chance to revise. And the way that I will grade it is that I will tell you as specifically as possible, what you might be missing so that you can fix it. And when you do your revisions, please use track changes and please leave my original comments in. That way, if there's something that I forgot to mark, I don't hold it against you when I reread it. I figure it's fair both ways. Cool, cool. Glad you like that. Yes, responding to revisions, doing revisions in response to feedback is a really important skill, no matter if you're in academia, industry, or anyplace else. So I want you to get a little bit of practice in doing that. Okay. Any other homework or project questions, written assignment questions, since we're on that topic still? All right, then I'll head back to my other question. What are cross-classified models for? Nathan says cross-classified experimental units are not nested according to levels. There's still a little bit of nesting going on, but what makes this different than what we've been talking about up to this point?
That we have more than 2 groups at level 2, more than 2 kind of entities.
More than 2 kinds, yes. So when people can belong to more than one cluster. Yeah, so there's different kinds of nesting that don't nest within each other. Yes, all of those things are correct. So the exact name that you would give to the situation sort of depends on the exact combination, but in general, I would think of cross-classified as when there's more than one kind of clustering. So in this example, we have students who we kept track of what primary school they were in, and we're keeping track of what secondary school they're currently in. And because not all kids go through the same school options, those are crossed dimensions at level 2. The example I had in the slides was kids in neighborhoods. If not all kids who go to the same school live in the same neighborhood and vice versa, then those are two different types of cross dimensions at the same time. People can also belong to more than one cluster of the same type. So if you have a longitudinal study, for instance, and somebody changes schools, that's sometimes known as a multiple membership model instead, because you can give them a weight essentially that conveys how long or how much they were a part of each different type of cluster. So if you have like patients who are seen by different doctors, or students, like I said, who change schools, something like that, these are the types of models that you would want to look into when there's more than one kind of clustering at the same time. Indeed. Do you think this is going to be easy or hard to fit in syntax based on the foreshadowing we did last time? So? Hard, yo. Yeah, this is an opinion question. There's not a correct answer to this. It sounds worse than it is, I think, because once you see the code, it's like, okay, I think I see where this is going. And they point out we only had 9 slides. Yeah, that's not because it's easy so much as I don't have time. Like this class could become 2 semesters quite easily. And so I got to make choices as to what I spend time on and what I don't. And I wanted to fit the generalized unit in, and I definitely wanted to fit the multivariate stuff in because that's becoming increasingly common across disciplines. So those are the things that I decided to prioritize. But I gave you some resources in case you're in this situation as well. So these data that we're going to be looking at here came from the Hawks multi-level modeling book. He has, I think it's in its 3rd or 4th edition by now. This is from, I want to say, the 2nd edition, 2012, chapter 7. So this outcome that we're looking at is some kind of measure of academic achievement in the 9th grade. These are children who are nested within 50 level 2 primary schools and within 33 level 2 secondary schools. So there are exactly 1,000 children, which also makes me think these data are simulated. The only predictors that we have pertain to a school characteristic, whether it was, as the textbook said, denominational, which I think means whether it's a religious school or not. They didn't really clarify that, but that's what I'm going to go with. So whether it's some kind of private school based on religion or whether it's not. And then child socioeconomic status, which is measured on a scale of 1 to 6 here. One thing that's complicating this particular design is that in this case, the number of students who are nested within a unique combination of primary and secondary, it ranges from 1 to 6. So there is a potential for what looks like a random interaction in this analysis, meaning that there would be an extra correlation of students who go to both types of schools in common, above and beyond just the correlation expected from each dimension separately. One last thing that I want to note is that the models that I'm presenting here do not follow the models in this chapter. He fitted smushed effects for SES. And the reason that he did that, I think, is because he simulated the data that way. But given that in real life you don't know what the right answer is, unlike in simulation, I think it's good to show the proper procedure for how to do things. So I'm proceeding from the perspective as if contextual effects are going to be possible, because I think in most real data they would be. So any questions or comments before we dive in? Okay, so the first couple of pages here do a lot of data steps, but I wanted to make sure to show this part because it's important, and because if you're doing an individual data analysis for homework 4, you are going to have to do this part as well. One of the things that I ask for are level-specific descriptive statistics and correlation matrices so that you can do some bivariate and univariate data description as part of your method section. So knowing how to do that, obviously a prerequisite. So I'm showing Stata code first. As usual, I dumped this into an Excel data set so that you can see exactly what it looks like. Here are the labels. So we have 3 different ID variables in this data set. Child ID keeps track of level 1. P, school ID, is primary school, which I think means grades like 1 to 8, essentially, in the American schooling system. Secondary school, which would be analogous to high school, 9 through 12 or 10 through 12 in most places. Achievement is the outcome. Child SES is a level 1 predictor. And then we have the denomination status of each type of school, whether it's religious or not, where not is the reference category. So those are the variables that were in the original data set. But to be able to analyze these data, we have to make a bunch more. So first off, achievement ranges on a scale of like 4 to 10. SES ranges from 1 to 6. This is the original student level data. So then I have 3 different examples of the same type of idea, summarizing the data across students who belong to the same type of clustering. So I did it first for primary schools. So in Stata, that's one line, which is nice. So the first thing that I did is build using a count function to figure out how many students each different primary school had. Then I asked it to give me a primary school mean for the 2 level 1 variables. Achievement is the outcome and SES is the predictor. PM today, by the way, stands for primary mean. So I'm breaking from my usual CM notation because CM is no longer specific enough. I have to tell it which kind of clustering we're talking about. So PM for primary mean. I then did the trick of telling Stata to preserve the current data set, then collapse so that I end up with a primary school level data set. So it's basically aggregating over all the rows that belong to the same primary school so that it becomes a constant. And then I asked for descriptive statistics and correlations. So here's the summary of primary schools, 50 of them. The number of students per school ranges from 10 to 31. And you can see the ranges on the other variables as well. It looks like there's a considerable difference in mean achievement as well as some difference in SES, although the extent of that is an empirical question. Then we get correlations. So this is an example of a level-specific correlation matrix. We're looking at school-level information and how it relates across the variables that we have. So for instance, the first column here is primary mean achievement, so that's the outcome, and that is correlated non-significantly positively with denomination status. It's not correlated with SES, and it's not correlated with school size. So those things are useful to know in the beginning of this process to make sure that the predictors that you put in are not too highly related. It's good to know what their bivariate correlations are to expect potential issues with unique effects not popping because things are too overlapping. Okay, with me so far? Fairly straightforward stuff. Fairly, relatively speaking, within class centered. Then we get means per secondary school. Same exact set of ideas, but now what we are aggregating over is unique school IDs for secondary. So I'm figuring out how many kids in each, getting secondary means for achievement in SES, building a secondary school level data set to get descriptive statistics and correlations, and then sending it back to the original form. So there's 33. In the book it said there were 30, but then when I actually looked at the data, 3 of the schools were labeled as both denominational and not denominational at the same time. So I fixed that to make it 3 additional schools, which I think was maybe what was intended, but I fixed it anyway. So we still see a little bit of differences in achievement with respect to the outcome, a little bit of difference with respect to SES, more than it looks like for the primary schools, just eyeballing it, and quite a lot of difference in how many children per secondary school. So somewhere between 4 and 48 is what we have here. Correlation patterns are somewhat similar. It looks like denomination status is not related to achievement. School mean, secondary mean, SES is not related, and neither is school size. Then we get to the unique combination. So now I have to do a couple extra things. So I am generating a new ID variable that is built from these two. That's a function I found in Stata, that was nice. Then I'm getting the number of children per unique combination. The PSM, which stands for primary and secondary school mean, for achievement and for SES. So the idea here is that we want to allow for the possibility that children who have common nesting in both primary and secondary schools might be more alike than just any rando child that goes to the same secondary school as another rando child. That's an empirical question, and the prerequisite for testing it is whether we have more than one observation. And so that's what I wanted to figure out. So going through the same step of collapsing, aggregating by unique IDs here, and then getting descriptive statistics. And lo and behold, yes, the number of children per unique combination of school type is 1 to 6. So that means we do have a potential for a random interaction. If we only had one unique if we only had one child per unique combination, then we would not. Then the interaction of secondary by primary school would have to be part of the residual because there's no way to pull that out. And here we have a different result with respect to bivariate associations. The mean SES for the unique combination of primary and secondary school is positively correlated with achievement. And the only other variable I had measured at that level was the size of the school, which was not. But look how many observations we have, 652. That's out of 1,000 kids. We have 652 unique combinations. However, if we drill down into the frequencies, 60% of these unique combinations only have one kid. That's going to cause some issues. So a few of you in your individual data analysis plans mentioned that you have clusters that might only have one person in them. Does that sound familiar to folks? Some of you have clusters that have one person, only one kid from that school, or one kid who sees that doctor, or one kid who lives in that town, that kind of thing. If that's your situation, where do you think that child's information is going to count? Do you think it would count at the within level, or do you think it would count at one of the between level 2s? So going back to just straight clustered, like if I have students nested in schools, if I have a case where there's only one kid in a school, can I keep them in my model? Can I keep them in the analyses? What do you think? This is a thumb question. Yes or no?
That would be incorrect, right? We could keep it, but then we would be assuming that the school information for that specific school in reality is information from the student, right?
Mm-hmm. Yeah, we can keep it. Now, whether you want to keep it is a different question. I have a comment. He is the school. That's exactly right. That's the problem. If you have one person per cluster, then that person's characteristics are the cluster characteristics, and that person's information goes up to level 2. So that's what's happening here, is that for all intents and purposes, 60% of these unique combinations are single people. So that's why we see a different pattern of result. SES is going to be related to achievement, but what I'm labeling this as with respect to the mean of primary and secondary school unique combination, in 60% of the cases, that's one kid. He is the school, exactly. Or in this case, the child is the unique combination. So that can mess up conclusions, especially with things like interclass correlation, where you're thinking of it as between differences, but if you have a child who is the school, it's not, it's kind of weird to think of that as between. So long story short, can you have singletons? Can you have one person per cluster and keep them in the model? Yes. But that can somewhat artificially inflate the amount of variance you have at level 2, because that person is a school at that point, or is a cluster. Beyond that, just controlling for cluster size might be something you'd want to do anyway. So assuming that your sample is representative with respect to differences in cluster size, keeping track of the number of people who are participating in your study from that cluster could be something meaningful just beside the point. So that's something to think about in terms of the covariates you might want to consider. Okay, questions or thoughts on any of that? Yes, go for it.
Lisa, so could we think of those numbers in the frequency column as cells? Because to me, we have like a giant contingency table between these two kind of groups at level 2. So to me, those numbers in the frequency column would be like the cells with that specific combination, right?
Exactly right.
Okay, great. Thank
Yep.
you.
So if you have like your 50 primary schools on rows, your 33 secondary schools in columns, then this is the number of people like per cell, and 60% of those cells has one person in it.
Got you. Thank you.
And next up then is 185 have only two. So we've just accounted for 88% of the cases with only two. So the idea of, is there an extra correlation among children who have both types of clustering in common? That's going to be tough to answer with the data set that's structured this way. We don't have a lot of information. We don't have a lot of overlap. If that's something you really wanted to know, you would want to go to greater trouble to get more people who have both types of clustering in common so that you can really start to pull that apart. I don't think that was the intent of this example. The intent of this example was just to demonstrate two-way crossing. But the way that the data were simulated allows us to potentially look at the interaction as well.
Lisa, and here we are also assuming that they didn't move, right?
Yeah, this is
These
cross-sectional.
things
Nobody's
are
moving.
fixed. Okay, great.
This is one data point, and everybody is in one school for primary and one school for secondary, and there's none of that additional complexity that you might see in real life.
Thank you.
Next up, making predictors. So I went back and forth in terms of how to set this up, and I decided to take the easy route because this was going to be complicated enough. And I have what are going to become three contextual effects of SES. I have the primary mean for SES, so that's the mean of all the children who go to that primary school. The secondary mean of all the children who go to each secondary school, and then the mean of the unique combination, which I'm labeling PSM for primary and secondary. And then at level 1, I'm going to have SES, and based on the scale of 1 to 6 for this variable and the fact that the overall mean was somewhat close to 4, I picked 4 as my centering constant. Would it change anything about my story if I picked 3 instead? What do you think? No. It would only change the fixed intercept, and it would change the moderator variable slopes interpretation if I added interaction terms with any of these things. But otherwise, whatever constant you pick does not change the story. But because I will eventually want to look at random effects, I also did within centering. So then here's the question, how do I do this if I have multiple clusters? The way that I first thought to do it was to take the original level 1 predictor, so child SES, and then I thought, well, maybe I should subtract off the primary mean and I should subtract off the secondary mean. When I did that and I looked at correlations with those means, they were not uncorrelated as I had intended, so that's not right. So then I'm like, all right, let me try something else. And what I eventually figured out is that this is the right answer right here. So I made the other two just to make a demonstration about this. In order to really identify purely within cluster variance, it has to be within the unique combination in this data set, given that there's more than one child for some of the unique combinations. So here's a correlation matrix for the student level data, the child level data here. And I highlighted a couple of things. So as expected, the mean for the primary and secondary school combination is correlated with each of the separate means because they're getting at the same idea. Within primary school SES is correlated with secondary mean SES because that's the other clustering, and vice versa here, but only for the combination where we've centered within the unique combination of both schools is the within variable completely uncorrelated with its corresponding mean. So that's the way to really make a within effect, is it has to be both in this case. So that's something I learned in putting this example together. All right, I know that was a lot of data description, but the idea being if you can aggregate over the cases that belong to the same cluster, then you can look at descriptives and bivariate correlations at that level. If reviewer 2 wants you to report a correlation matrix at level 1, you would want to be upfront about the fact that those are smushed correlations. So that's why I think level-specific correlations would make more sense. This correlation matrix, what I was trying to demonstrate was the conditions under which a within variable is uncorrelated with its cluster mean as intended, and it doesn't work unless you within center relative to the unique combination mean. All right, R folks, I didn't leave you out. So I got some good news and some bad news. I can do all of this in R with a little bit of help. Thank you, Jonathan. But his pseudo R-squaredinator function does not anticipate crossed models. So I asked him, like, is this something that like you could spend 30 seconds and fix it? And he's like, no. I'm like, okay, so it's more complicated than that. So here's a challenge to those of you who like coding. Fix the pseudo R-squaredinator function to work for cross models, and I will be eternally grateful. Okay? Apparently it's harder than it sounds because you have to build in catches for every type of possible situation. But if there's a way to do it that would work for this, those of us who use these functions would be appreciative. So that one's still under development, so it's not inside the folder because I'm not using it for this. Instead, I'm using the macro in Sass, and then inside the example file download folder, I have an Excel sheet that does the same thing. So low-tech options for getting the same information. So reading in, add unit means is the one function that we're using here. So we're adding means for primary school, then getting descriptives and correlations, doing the same thing for secondary school, getting descriptives and correlations for those variables, and then building a unique ID, which the way that Jonathan helped me do this is to basically take the primary school and make that the first part of the number, and then put a decimal, and then make the secondary school the next, but making sure to pad it so that 0.1 and 0.10 are viewed as different things. So that trick seemed to work reasonably well, and so we were able to get descriptives and correlations for the unique IDs as well. And then here's the same type of centering and some correlations within the student level data. So all the same stuff. And for those of you who would like to use Sass, I have the Sass code that does all of this in the download folder too. Okay, ready to see some models? Woohoo! It's not just the Novocaine talking. I get this high for multi-level modeling any day of the week. So I'm taking a break from the placeholder multi-level notation for today. Can you guess why that might be?
Because level 2 is not as clear as before.
Yeah, which level 2? Right? I'd have a level 2 primary set of equations, a level 2 secondary set of equations, a level 2 interaction potential set of equations, and I could figure all of that out. But then the question is, where do I stick the fixed intercept? Because they all share it. And it would not be correct to stick it in multiple places because that would imply that it contributes to predicted outcomes multiple times, and that's not how intercepts work. So regardless of how many different kinds of random intercepts you have in your model, you have one fixed intercept. That's it. It is the same idea, by the way, in psychometric models, latent trait factor type models. No matter how many different factors are predicting an item response, that item still only has one set of thresholds or one intercept. It's the loadings or the discriminations that you would have more than one of. So analogously here, no matter how many different kinds of random effects I have one fixed intercept. So for that reason, because level 2 gets messy and it's unclear which one should get the fixed intercept, I'm going with just straight composite notation where everything is in one equation. The way that I've opted to do this, though, and I had to break my rule about what C and P mean, and I'm sorry. Just can you accept my apologies for that? No, Kendall's not having it. Like, you cannot change what C and P mean. No, not doing it. I had to do it, though, because IJK is insane. I will not ever IJK my papers because J and K don't stand for anything, and I could be individual. Individual child, individual school, individual what. So I went with CPS. That does not stand for Child Protective Services, although some of you might feel like they should be called after today's lecture. CPS stands for child, primary, secondary. IJK is individual. Just kidding. I like that. So one of your levels would be just, and level 3 would be kidding. And then level 4 would have to be like, seriously. But no, CPS. So the subscripts follow the order of, is this a child variable? Is this a primary school variable? Or is this a secondary school variable? Where for each, we start counting at 0, and then we add numbers as we add terms. So this is gamma 0, 0, 0, because it is the fixed intercept with respect to all the dimensions at the same time. Next up is U0, which we're used to seeing, but it's U0, P0, because P is what this varies over. And then we have E, which is our level 1 residual we're used to seeing per child, per primary, per secondary. So this is a 2-level empty model. We are assuming that primary school matters. So the random intercept for primary school in turn induces a correlation of children who went to the same primary school. But I don't have any random intercepts yet for secondary. So if I don't have a random intercept for secondary, what am I saying about the relationship of children from the same secondary school, according to this model?
Zero?
Cheers. 0, yeah. In other words, I'm trying to say this as many different ways as possible. I am assuming no dependency related to secondary schools. The only source of dependency has to do with which primary school they went to before and not where they currently are. That's what I'm saying. That's a testable hypothesis. So this model then is like what we're used to, where we have P school ID as the only source of random effects in both Stata and R Elmer as usual. Get my variance out. Looks like both of them are reasonably sizable. Ask it to give me an intra-class correlation, and it's 0.23. So 0.23, according to this model, is the expected correlation of the children who went to the same primary school. There is no expected correlation of children who went to the same secondary school yet. And if I want to test this intra-class correlation for significance, the way to do that, as usual, likelihood ratio test. So this compares a model without that random intercept variance, so just an E-only single level model, assuming no dependency of any kind, and the difference in -2 log likelihood is 170. So regardless of whether you worry about a mixture chi-square distribution for that, it's wildly significant. So yes, 0.23 is not 0. What are we doing? So yeah, empty models are old hand by now. You've got this. Now, next up, again, in yellow, because I know in week 10 of the semester we could all use a little help. So I've added UOOS, because S is in the 3rd place. So that's why it's 2 zeros before it. This is adding a crossed intercept at level 2. So another level 2 dimension that keeps track of which secondary school a child is currently in. So this is now called a cross-classified model, or a crossed random effects model. I have 2 different level 2 types of clustering. They're orthogonal, so the U's are not correlated, and they're also not correlated with E, the level 1 residual. Now explaining the code is going to take a second. I have a link to the Stata manual that describes this, and also the specific slides where Don Hedeker talks about this. But what you have to do to make this work in Stata is a trick. So do you see, Stata folks, this underscore all colon r dot school thing? That looks different than usual. That takes a minute to explain. But let me answer a question before we do that. Vladimir, go for it.
Lisa, can you repeat what the interpretation of our residual at level 1 will be?
Yes, I did. I don't think I said that, so I'll say it for the first time. So E then are remaining differences between children after you control for which primary school they went to and which secondary school they went to. That's the way I would think about it.
Okay, now, but that residual is specific to the unique combinations or just for all students in our dataset?
It's for everyone.
For everyone, okay.
So the way that I would think about this is that the fixed intercept is like the mean of the primary means and the mean of the secondary means at the same time. And then you get a bump for which primary school you went to. You get a bump for which secondary school you went to. And then E is the remaining difference to get to what your actual outcome for achievement would be. So it's within both types of schools.
Great.
Yeah. Okay, so how to set this up. Multi-level modeling software packages, the earliest ones, so I think HLM worked this way. There's a European one called MLWin that I don't think is as popular, but except folks in Europe still use it quite a bit. And Stata fall into this category. They're not designed for cross models, but some genius figured out how to hack it. There's a hack for everything, right? What this is doing behind the scenes is creating dummy codes in the data. I don't think you actually see them, but if you ever had to do this for real without the hack being implemented, this is how you would do it. I think I have a slide on about this somewhere, or else he does. You would create as many dummy codes as you have unique level 2 units for whichever dimension you're deeming as the cross dimension, and it should be the one that has fewer possible to make it go faster. So because there are only 33 secondary schools, but there are 50 primary schools, I did the hack for the smaller dimension. So what you do is create dummy codes for each one. You create another column that is just a column of ones. And you say that that column of ones is level 3 of your model. And with nested under that is this set of dummy codes. So R.S is referring to the set of, it'd be like 32 dummy codes. And you're saying that each of those has the same amount of variance and there's no covariance. The end result of it is that it operates like a cross model. So it's a fake level 3 because in Stata, the levels are assumed to go from the highest to the lowest. So if you see this bar thing, it thinks that's level 3. Whatever comes next, it would think is level 2. So it's a trick to pretend like we have a third level, but we really don't. And I've seen various combinations of this in practice. It took me forever to actually get it right. And this example is the first time I've ever gotten it right in terms of adding random slopes to this type of model. So again, thank you, Don Hedeker, for figuring this out and helping the rest of us to do so. So from the user's perspective, you just have to remember to add this weird all prefix thing, but otherwise it works the same as what it does in programs that are designed for cross models. So SAS, SPSS, Elmer, I found all run super fast with cross models. They don't have a problem with it. In Stata, it takes a minute. It's not like the estimation did not anticipate this, so it does chug along a little more slowly, but it does eventually figure it out. Okay, Stata folks, is that clear enough? I realize it's not super clear, but it's like, okay, I can copy this. I'm capable of copying this and changing the ID variable, and that's really all I'm asking. Just R dot, just stick that thing in front of it with the L. Yeah. So I pasted in the Stata output so that you could see that it does look very much similar to what we would get out of R or SAS. So the fixed intercept here is 6.34. That's the average achievement across primary schools and secondary school means. Then you get your random effects parameters. So that 0.078, that's my random intercept variance across secondary schools. Then the next section, 0.17, is my random intercept variance across primary schools. Those are both at level 2, but they're not related to each other because they pertain to two different kinds of clustering. And then at level 1 are child-to-child differences within the same school, and that looks like to be the largest share of the variance. So just eyeballing these things, it looks like there's more variance across primary schools than there is across secondary schools. And we can do some descriptive effect size-y kinds of things to try to quantify that as well. All right, Stata folks, what is this telling me right here? We talked about this before. Is this useful information or no? Not. I like the X sign. It's like you're on a game show. Nope. chi-square 2 degrees of freedom. That is the clue. It's not a good clue, because if this were easy to understand, then I wouldn't have a job. But thankfully, it's just hard enough to where we can figure it out with a little bit of help. What this LR test versus linear model chi-square is telling us, the 246, is a likelihood ratio test against a model without either of the random intercept variances. So this is always against a straight up regression model with only E. So this doesn't answer the question as to whether we actually need this new second random intercept variance. To do that, we have to do the likelihood ratio test ourselves. And I went ahead and did that using LR test, and the test statistic is 75, meaning yes, we do. In R, I highlighted the new dimension at the end here. 1 for secondary schools means give me a random intercept for that dimension as well. And I don't believe there's any assumptions in R with respect to nesting of level 3 versus 2, although I could be wrong. But at least the way that I wrote the code, these are both level 2 and there's no ordering to it. So here's the new variance component, random intercept for cross secondary schools. I did my RANOVA to try to figure out whether we need it. So the first test here is what happens if you take out primary random intercept variance. We already learned that that was significant. The second is what happens if we take out the newly added secondary, and that is significant as well. So it looks like we do need both. Okay, how are we doing? I want to direct your attention to the amount of residual variance in this model versus the previous model. So the straight up 2-level nested model had a level 1 residual variance of 0.77. After adding the secondary random intercept at level 2, that 0.577 was reduced to 0.505. Coincidence or consequence? So residual variance for child-to-child differences was 0.577, and the model that had 1 random intercept, it is lower now at 0.505, and the model that has 2 random intercepts.
Always consequence.
It is always consequence. I thought about changing it up once in a while just to keep you all on your toes, but then I thought, no, week 10 is not the time for that. But what's happening?
We are repartitioning residual variance
Exactly
to
right.
create pile of variance. Okay.
Yep. So once upon a time there was an E, and all the variability in the outcome was in one pile, and the first thing we did is pull primary variance out of it. What we've done is now pull secondary variance out of it. So the level 1 residual variance has to go down because part of the variability that we thought was child-to-child differences is actually due to which secondary school they went to. Now, would I compute a pseudo R-square type of statistic for this reduction in variance? Do you think that would make sense? Not to me. There are other people to whom it would make sense, and those are called conditional R-squares rather than marginal, but I would argue it does not. Functionally speaking, these 3 piles of variance right here are error terms. We don't know why it is that some secondary schools have higher achievement means. We don't know why some primary schools have higher achievement means, and we don't know why some kids do either. So these are all 3 different kinds of error from the perspective of we haven't explained variance, but what it does tell us is which kind of variance is relatively more salient. Just eyeballing these numbers right here, if I want to have the best shot at explaining variance in achievement, what kind of information do I need in terms of predictors? Finger question. Yeah, level 1. Kid thinks. Now these numbers, you can judge the relative differences between them, but to make them more absolutely interpretable to an audience that is not familiar with this particular outcome, we can change them into proportions. So that's what I did here. So I computed this in SAS so that we could make a nice happy little table. Here are the 3 original variance components, the actual amount of variance due to the 2 random intercepts and the level 1 residual. I summed them to get this number right here called total. You are allowed to do that so long as your random effects are uncorrelated. So each of these is uncorrelated with the other, you can take a sum. And then I figured out what proportion was due to each. And so the math behind the table is down here. So if I work in terms of proportions, we have 23% of all the variance in achievement has to do with what primary school you went to. Only 10% has to do with where you currently are in your secondary school. And the lion's share of it, about 67%, has to do with which kid you are. So to your reader, do them a solid, give them this information. Give them these three proportions. Because then they will be able to compute any kind of interclass correlation that they want, even if you don't give them the one that they're looking for. Guess how many kinds of interclass correlations there might be for this? One or more than one? There's at least two and possibly more. So at this point, when you're in crossed model land, or when you're in three-level model land, anytime you have more than one kind of random effect, give your readers proportions to work with. They'll thank you. So I took those proportions and I saved first the results of the variance components into an object in R. So I did this in Excel as well, but for those of you who are using R, it can be helpful. And the object looks like this. So you have to understand what this looks like in order to understand the code that follows. So the first thing that I did is compute the total, which is the sum of this column right here under VCOVE. So row 1, row 2, row 3 for column 4, which in this little table, this is the fourth column. So I'm computing the sum. Then I am computing intraclass correlations of each kind based on the different rows. So the first row is primary schools, the second row is secondary schools, and the third row is child residual. So the way that I would interpret this then is that 0.23, the proportion of variance here, that's the expected correlation of children who went to the same primary school but went to a different secondary school. Because that's only the correlation that's being induced by the random intercept for primary. Likewise, the proportion of variance due to secondary schools is also the interclass correlation of children from the same secondary school but not the same primary. That's only 0.10. And then we have the unique combination intraclass correlation, and this is additive. So what is the extra correlation that you would see if a child went to the same primary school and the same secondary school? We can add those components together and it works out to be 0.33. So this model says that we expect a stronger relationship for kids who share both types of clustering. And it's assumed to be an additive relationship. Okay. Does that make sense? Put out the table here. Or questions, if it doesn't. We're good? So basic principle is still the same. Intraclass correlation is always some kind of proportion of variance out of some kind of total. It's also the expected correlation of level 1 units from the same whatever. So given the cross classification, there's 3 potential intraclass correlations here. And if you're like, can I just do less typing and get this? The answer is yes. All you have to do is this in R, the ICC function within the performance package. If you add the option by group, then it spits out the interclass correlations for each of the level 2 units by themselves. And if you just ask for straight ICC, you wouldn't know that, but what it gives you is actually the combined. So what it's counting as the ICC is for children who went to the same school of both types. Descriptively, I can also talk about variance across different types of schools using random effect confidence intervals. So I built those as well. So the center is the fixed intercept. The range around it is given by 2 standard deviations of the random effect variance. So the school means across primary are expected to differ within this range for 95% of them. The school means across secondary are expected to differ within a narrower range because it has less variance. So this can help to describe sort of in relative terms, what that extent of variability means, what 10% means versus 23%, that kind of thing. Okay, 1:30. How we doing? And to think I worried that I wouldn't have enough stuff for today. You would think that I would know by now that I just cannot estimate time to save my life and that everything takes 3 times as long. But no, maybe I need to teach for another 20 years to figure that out. Okay, you ready for the crossing? Question, is there a shortcut in Stata to look at correlations within the groups? When I tried to do the ICC function, it yelled at me and said no. So I don't know that there is. Once we get to 3-level models, though, then you can ask for ICCs, but the ones that it gives you are not the ones that you want. So the moral of the story is do the math to check what the program is doing to make sure that it's doing what you want it to, and then you may have to do math if it doesn't do it. But no, Stata yelled at me. It was not having it. VCore and SAS, by the way, on the random lines will give you these as well, but you got to dig through a ginormous table to get them. All right, crossing. So do you remember back at the beginning we were worried about the fact that there are between 1 and 6 children in each unique combination of primary and secondary, and that could be an actual thing? Empirical question. So I'm adding a third random intercept. This is sometimes referred to as a random interaction. It is an intercept that is common to the people who had the same primary school and the same secondary school. So this is introducing an extra source of correlation and asking whether that's significant. To do that, I built a new ID variable called unique ID that I put into Stata. I did the same thing in R, and in SAS you don't have to do that. You can just say primary star secondary and it works. It does unique combinations as multiplicative. So here's the solution. My new variance is quite little. It stole from the residual variance as expected because now I'm repartitioning. So this is a 4-pile model instead of 3. However, it looks like the addition to the model did not improve fit. Adding this extra random intercept variance did not make my data significantly taller. So I'm going to cut it out to avoid convergence problems. But before I do, I wanted to show you how the interclass correlations formulas would change as a function of that random interaction being included in the model. So now their total is across 4 things. The interclass correlations for primary school and for secondary school are roughly the same. That's not a coincidence. What we've done is reallocate the residual but left those alone. So they wiggle a bit, but they don't really change. Whereas the expected interclass correlation of students from the same primary and secondary now picks up that interaction term. So there's an additional, actually it's the first one, there's an additional component to the correlation that results from including the random intercept for the primary by secondary interaction. So that number is 0.367 according to this model. Previously, without the interaction term, the same interclass correlation was 0.33. So another way to think about this is that the likelihood ratio test being non-significant means these numbers are equivalent. Assuming that there's an basically not allowing an extra correlation is sufficient according to these data. So we'll stick with just the 2 U's. Now I did the same thing for the SES predictor. It's a continue-ish variable, so I used mixed and Elmer the same as usual. And I went ahead and tested all 3 random effects, one for each type of school and the interaction. And here's what happened. I get the unhappy convergence code error. Can you guess why I got that? Does anything in the output strike you as problematic? Is R just messing with me, or is there like a legit complaint that it might have?
Did you define the IDs as factors, or did you keep them numeric?
I did not define them as factors in the data.
That might be why. I'm not just off the top of my head.
Okay. I have seen people do that, but to me, it never seemed to make a difference, and so I didn't bother. Another idea of variance is 0. Yeah, this. This is the problem.
Oh. Whoops.
Yeah, this is a whoops. So this is how I know how the data were simulated, quite frankly. This is the SES child level predictor. He created it to not have any level 2 variance. So R is mad at me that I'm trying to estimate a variance and it's turning out to be 0. So I don't know if there's an option in Elmer to let it go negative. In SAS you can do that, but it's not a good idea to as a general principle. But yeah, this is, when you get this sort of message, you will get error messages that say things like non-positive definite. That refers to your matrix of random effect variances and covariances. That means that one of your variances went to 0 or one of your correlations went to -1 or +1. So something is awry and broken. So yeah, it's not happy about this. However, what's interesting is this one right here. The unique combination one is not 0. And I think that's because in 40% of the cases, there's only one child per unique combination. So functionally speaking, that's still kind of like level 1 residual variance. So based on these results, if I were doing this analysis in reality, that this would mean that I really don't need to worry about contextual effects, but to demonstrate proper procedure, I'm going to go ahead and worry about them anyway. So the intraclass correlations, by the way, are non-existent in this. And the likelihood ratio tests all say that not a one of these is significant. So SES is primarily a child variable in this data set. All right. How are we doing? I think my face is working again. It's nice. Blah, 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 blah. You are here. See, I can see you smile and laugh. It's stats. I gotta throw out all the stops. And it's Thursday, too. So I went ahead and added some predictors. These are school things. We got the primary denomination, secondary denomination, where 0 means it's not religious and 1 means it is. And I also went ahead and threw in the interaction term because why not? This will be the last model for today, I promise. So note the subscripts. For this one, it's 010, because P is in the middle. And 1 comes after 0, as we established last time, right? This one is 001, because it's a secondary characteristic, and this is the first predictor of the secondary characteristics. And then this is 011, because it's both. So I went ahead and included an interaction term. So I can throw those fixed effects in the same as usual, 2 main effects and their interaction. Same thing in R, and survey says nothing is significant. However, it looks like denominational schools would have higher expected outcomes, but not significantly. And it looks like the effect of being denominational gets stronger if the other school is denominational as well. But here's my last question for you, okay? This table right here is from SAS. This is the change in each of the variance components after including those 3 predictors. So this is what they were. This is what they are now. And this is the pseudo R-square for their proportion reduction. So the first variance component refers to the random intercept for primary schools. Which fixed effect do you think made that go down 1% or so? You got 3 choices right here. Primary denomination, secondary denomination, or the interaction. Focusing first on primary school random intercept, which of the fixed effects was responsible for that reduction in variance, or should have been?
Primary?
Primary. And how do you know that?
Because that's the effect related to that specific type of group.
Yep. So primary is a primary characteristic. Its job in the model would be to explain why there are mean differences between primary schools. It explained 1% of the variance, which was not significant. How about the next one? Variance across secondary schools and mean achievement. Which of my 3 fixed effects was responsible for explaining 7.8% of the variance? Don't think too hard. This is softball, I promise.
Secondary, right?
Secondary. Now this is kind of a decent effect size, right? 8%. Why do you think it's not significant? Okay, it's not my last question, but it's like the last topic, I promise.
Power?
Or, I got 1,000 kids. How do I not have enough power for this? There's only 33, Hillary says. That is correct. It does not matter that I have 1,000 kids. What matters is that I have 33 secondary schools. So my power to detect differences as a function of secondary school characteristics is tied to a power based on the sample size of 33. Yep, that's why. The same thing is true for primary, although not quite as bad. We have 50 primary schools, but that's still not a lot. So keep this in mind when you're designing studies. The number of units you have still matters with respect to power for predictors of that kind. Last but not least, I got a teeny tiny little part of the residual. What do you think was responsible for that? There's only one left. Interaction term. It does not have a random intercept variance to explain because that would have been the random interaction that we kicked out. Where that random interaction came from was level 1 residual, so that's what it goes back to. Ta-da! Aren't cross models fun? No. Okay, 142. I think that's enough for today. What about you? Question? That's what I was going to ask. Does anyone have
Yes.
questions before we go? Yes, hit me.
A quick one. So if that interaction between those random effects wouldn't be there, but we included the interaction in the fixed part, what would be the role of that interaction between our level 2 variables in terms of the random variances?
They would explain level 1 residual if there's not a random interaction intercept.
Really? So, okay, level 1 instead of any of the level 2 random variances.
Yep, because
Wow.
it's the unique combination of the two. So it's
Yes.
not either one by itself, it's the combination, and the combination is buried in the residual right now.
Oh, yeah, that makes sense. Great. Thank you.
Because it was a teeny tiny number that wasn't significant, so we let it stay buried. But that's what it would be doing.
Gotcha. Thank you, Lisa.
Yep. All right, other questions? All right, then what are folks working on between now and Monday night? Homework, unless you did it already, in which case you can take time off. But let me know if you need help with homework. Remember the rule, 15 minutes on the same problem means you stop and ask for help. But before that, stop and read the instructions. And if that doesn't fix it, then please ask for help. I'll be checking email over the weekend, as I always do, especially when there's a homework. So you can email at any point in time. That's no problem. Office hours are also being held this afternoon and Friday and Mondays as usual. So, all right. Then thanks for being here. I hope to see everybody in person next week. Stay dry, stay real. Bye for now.